Perfect. Excellent. Very good. So today we'll continue with our discussion of effective theory. Before starting with new material, I thought it would be good to recap a little bit what we discussed yesterday, because most of what we're going to say today is going to build on what we discussed yesterday. So the first thing we've seen yesterday is that actually the defining ingredients of effective field theories are quite simple, quite easy to state. There are three main ingredients to specify any effective field theory. You need to specify the degrees of freedom, which means, in a field theory, means what fields you have around. The symmetries that constrain the form of the effective action and the form of the dynamics, and how your degrees of freedom transform under these symmetries. And finally, the third, and so based on just these two ingredients, your effective action is going to contain an infinite number of terms in principle. But what comes to the rescue is the third defining ingredient, namely a series of expansion parameters. And we saw that each term in the effective action should be associated, should be given a very definite scaling in these expansion parameters, so that if we know up to what accuracy we want to calculate, we can figure out from the get-go which terms we should include in the actions and which ones can be safely dropped, because they will give rise to corrections that are negligible for our purposes. So we illustrated some of these ideas in the context of this toy model effective theory defined by this Lagrangian that includes a scalar and a fermion field. The scalar, just to remind you, was a pseudoscalar. And we said we were interested in working in a regime where we can trust perturbation theory, so where the couplings y and lambda are small. And we were also interested in a regime where there was a large hierarchy between the mass of the fermion, the energy of the processes we were interested in, and the mass of the scalar, which was the heaviest of the two fields. So we saw that in this regime, at energies much smaller than the mass of the scalar field, we can describe exactly the same physics, both at 3 and also at 1 loop order, and the procedure can be carried out at arbitrarily high loop order. We can describe the same physics using an effective action rather than the full action that describes both the scalar and the fermion. And I showed that you can get the same results, say, for the 2-point functions, and therefore we calculated just, we focused on the quadratic part of the effective action. And it looked like so, okay, with these three terms and these coefficients, these Wilson coefficients that had the following expressions. I didn't write them down explicitly last time, but I wrote down, I think, the zero part of the effective action. And then I discussed how, in order to match the loops, we needed also a 1 loop correction. Okay? So now I've added these two contributions together in a more compact form, because it's going to be helpful for what we're going to talk about today. Now, as I said already, each term in the effective action is associated a definite power counting scaling in powers of the energy over the mass of the scalar. And in order for that to work, we need to work in dimensional regularization. So our 1 loop diagrams naively will be UV divergent, but we regularize them in dimensional regularization. And then I chose to work with an MS bar scheme, which determines what exactly, what part of the 1 loop corrections you're going to absorb into the counter terms. So diagrammatically, we calculated these diagrams both in the EFT and in the full theory. Remember the second diagram in the full theory vanished. And we showed that, whereas, sorry, the first diagram here in the EFT was calculated starting from the 3-level effective action. And what we showed is that naively, this diagram and these diagrams actually give quite different results. I wrote them here explicitly. But that's okay, because the effective action also contains a one loop part. And at this order, this one loop part will give a 3-level, will contribute a 3-level diagram, which is precisely designed to account for the initial discrepancy between this diagram in the EFT and this diagram in the full theory. Okay. So by choosing the one loop part of the effective action appropriately, we can ensure that the EFT and the full theory up to this order in an expansion in powers of energy over mass of the scalar give exactly the same results for the 2-point functions up to one loop order. Okay. So this is, in a nutshell, these are some of the things we saw yesterday. And now today we're going to build on that. And the first thing that I will talk about is why effective theories are a useful framework to organize calculations in theories where there is more than one scale. Okay? So we're going to talk a bit about summing large logarithms. You'll see in a moment what this means. Okay. Very good. So, but before talking about that, let me just make some broader comments, which also further address a question that was asked yesterday. Someone asked whether the effective theory depends on the renormalization scale. And I was quick in pointing out that the couplings in the effective theory depend on the renormalization scale. On the other hand, though, something that I should have added to dispel any confusion is that the renormalization scale is in principle an arbitrary parameter which we are forced to introduce when we renormalize our theory. But because this is an arbitrary parameter, physical predictions cannot depend on it. And in order for physical predictions to be independent on mu, the couplings must satisfy some renormalization group equations, which determine how these couplings change if we change mu. Now, in practice, we are free to choose whatever value of mu makes our life easier. And so, for instance, you see that, let's look, say, at the full theory result, okay, which is this equation here in the box. You can see right away that there are some logarithms of capital M over mu. And so clearly, if we set mu equal M, the logs will vanish. And this expression will simplify. Okay. This is nice because if we keep an arbitrary value of mu, then we would find that higher order loop corrections in the full theory would contain terms of the form y² over 16 pi squared times the log of m over mu, or m squared over mu squared, the same, to some power n, where n is the loop order. And so, in a sense, this is when you perform a loop expansion in the full theory, this expansion will be well-defined, under control, provided this combination is small. And now you can see that if you choose a value of mu that is very different from capital M, so that the log is large, in principle, this expansion parameter is going to be large, or it's not going to be as small as if you chose mu equal m or close to m. And so your loop expansion naively would seem to convert much more slowly. Now, these logarithms in practice can be, if you want, resummed by considering by solving the renormalization group equations and considering the fact that the couplings depend on a scale. But that is just another side of the same coin, meaning this follows or goes hand in hand in the fact that in a theory with a single scale, there is one choice that we can make for the renormalization scale, in this case, mu equal capital M, which makes the log solve so that large logs are not around at all. Now, in theories with multiple scales, as is the case for our full theory, in general, you're going to have several logs around. And so, for instance, let's say we also have a small scale, a scale small m. So you can have also logs of mu over little m, or even logs of big M over small m. Okay. And so an example of the latter in this particular correction, one loop correction to the 2-point function is the one here in brackets. Okay. Now this one in particular is not that, it's a little harmless because it comes with some suppression factor in front that ensures that even if the ratio between big M and small m is large, this overall contribution here is going to be small. But in general, that doesn't have to be the case. And so the main point here is that when you have more than one scale in your theory, in general, there is not going to be a preferred choice of the renormalization scale mu that allows you to eliminate all possible large logarithms. Okay, and as I said, if you have large logarithms around, then you need to worry about the fact that your perturbative expansion is not going to converge as, it's not going to be as accurate as it could be. Okay, and for the same reason, because there is no preferred choice of mu, which avoids all large logarithms, the renormalization group by itself is not going to save us in this case. It's not going to be able to resum all these large logarithms. Now, this is where organizing calculations in an effective theory becomes a very smart thing to do. So let me show you why. And to do that, let's look at the way in which the effective theory is organized. Okay, and in particular, let's start looking at the Wilson coefficients in the effective theory. You see, the Wilson coefficients only contain one type of logarithms. They contain only logarithms of the mass of the heavy scalar, so the UV scale, divided by the renormalization scale. If you remember, something that I pointed out yesterday was that terms that were not analytic in the light mass, so in the IR scale, were exactly the same in the EFT loop and in the full theory loop. Okay? Because of that, when we do the matching and infer what this difference should be, what the one loop correction to the effective action should be, there is no trace of any logarithms of IR scales in here. And that is why in these Wilson coefficients, there are no logarithms of little m. Okay. So in here, we only have this type of logarithms. But then when we go and calculate the one loop correction, we only have another type of logarithms. We only have the logarithms of the renormalization scale divided by the IR mass. Okay, so this is very interesting and should be contrasted with what we found in the full theory, where instead we had at the same time this type of logarithms and those type of logarithms at disordered loop corrections. So what effectively the switching to an EFT brought us is that the logarithm of the UV scale divided by the IR scale was broken up into two pieces. Like so. Okay, so this is the logarithm I'm referring to. It was broken up into two pieces. This piece ended up in the Wilson coefficients. Whereas this piece was came about by calculating a one loop diagram in the EFT. And so because the logarithms are now split in between Wilson coefficients and then the loop calculation, this means that we can use a clever strategy to ensure that no large logarithms arise. Okay? And this is a two-step strategy. By looking at the expressions for the Wilson coefficients, you see that if we match the coefficients at the scale, which means if we calculate these z, m, and n at the scale mu equal m, capital M, so the UV scale, then there will be no large logarithms in this expansion of the Wilson coefficients. Okay, so the matching will be as accurate as it could be. So this is the first step. We're going to match at the UV scale. Okay. This means that you will know the couplings of the EFT at the scale mu equal capital M. And therefore that in principle, when you calculate now this loop in the EFT, the scale that you will need to use here would be also capital M, in which case you would have again large logarithms. But there is an easy way to circumvent that. We can simply run the couplings down from mu equal M by solving the RG equations down to the IR scale. Okay, so then we obtain some Z of M, M of M, and N of M. And then we can use these couplings, their values at the lower scale, to calculate loop corrections in the EFT. In which case now the appropriate value of mu to use here would be mu equal little m, and so we would avoid, again, large logarithms. So with this combination of first matching at the UV scale and then running down the values to the higher scales, we can ensure that in our final results, there are no large logarithms. Okay, so and this is one from a calculational viewpoint, it's one of the advantages of using an EFT approach. So maybe this is a good moment to pause and see if there are questions.
Yes, so there is a question. Let me read it to you. It's about the example that you were discussing at the beginning. So is there an assumed hierarchy amongst the y, lambda, and p squared over m squared?
So let's see, going back to this stage. No, not necessarily. As long as y and lambda are small, I can treat these expansions as independent. Then in practice, conceptually they are independent quantities.
Okay, so is there any other question? Yes, so there is another question asking, would you please elaborate on the MS bar scheme?
Yes. So, very good. So if you were to calculate a loop diagram, let me find, let me see if I can find the simplest. Yeah, so if you calculate, say, a loop diagram of this form in dimensional regularization, so in D slightly away from 4 dimensions, in 4 minus epsilon, one thing you need to make sure is that when you go to away from D equal 4, that your coupling constants remain dimensionless, and then for the coupling Y, should go to Y to some scale mu tilde to the epsilon power. So we're factoring out the dimension part to ensure that Y remains dimensionless, as it should. And what you find is something of this form. MQ m squared 2 over epsilon plus 1 plus log mu squared over m squared, where now this mu is related to mu tilde by some factor of square root of pi e to the minus gamma, where gamma is Euler's constant, times mu tilde. So now for epsilon that goes to 0, this per piece is UV divergent. And it's going to absorb by some counter term. There is some arbitrariness in what you want to absorb in your counter term. For instance, you could choose to absorb also this constant piece. And the MS bar scheme is simply a scheme where you rewrite, if you want, one way of saying it is that you rewrite your amplitude in terms of mu rather than mu tilde. And then the only thing you absorb in your counter term is the divergent piece. And every other finite piece stays in the, remains in the result. Okay.
So Riccardo, there is one more question.
Yeah.
In the one loop calculation, how can we have logarithm of capital M divided by small m when we expand the integrand in powers of capital M over small m?
Okay, this is a very good question. Now, this result is the one in the box, is the result in the full theory. And so this result was calculated by first performing the loop integral and then expanding the result in powers of energy over of P and little m over capital M. Okay. Instead, you can view the result in the EFT as what you would have obtained if you had expanded the integrand first and then calculated the integral. And in fact, you're right, in the EFT, there is no trace of a logarithm of large M over small m. And that's because by performing this assumption before, this expansion before integrating, we have assumed from the get-go essentially analyticity in big M, which turns out not to be a property of the full result. But that's okay because we can essentially recover these logs of big M by fixing the one loop part of the effective action appropriately. I don't know if that answers the question.
Alessio, is the answer okay? Yes, okay. Yes, he's satisfied. So there are no more questions for the moment.
Okay, then
so
then I'll continue. We're gonna switch gears for a moment, and I would like to talk about, in light of what we have, seen so far, about the concept of renormalizability. Okay. So I emphasized over and over again that to be kosher, in principle, your effective action should include an infinite number of terms, and many of them won't matter for given the precision you're interested in, but in principle, they're there, right? So how can we square this with the fact that usually in particle physics, I look at the standard model, the theories we looked at are renormalizable theory. Meaning these are theories in which any UV divergence can be reabsorbed, if you want, with in the couplings that are already in your action to begin with. There are no other terms that you will need to add. And in fact, the toy model that I started with, even though I haven't stressed that, was one type of renormalizable theory. Okay, so for historically, a lot of emphasis was placed on the fact that field theory should be renormalizable, should contain renormalizable terms, and this was thought to be necessary for the theory to be predictive. Okay, and essentially for two reasons. One, because say in 4 dimensions, the theory would contain a finite number of coupling constants. And having a finite number of couplings was viewed as a requirement for the theory to be predictive, because in principle, there is only a finite number of measurements that you need to perform in order to fix them. And the second one was that any UV divergence could be absorbed, swept under the rug. And so you could be left with a theory, with a result that was in the end finite, and you could compare with experiments. Okay? Now, we have already addressed point 1 repeatedly by saying that in practice, only a finite number of terms will matter because only the ones that scale with small enough powers of your expansion parameter will contribute a significantly to your result. So let me comment on on the second one instead. So in general, non-renormalizable interactions will give rise to divergences that can be absorbed only by adding more and more non-renormalizable interactions with the same field content and the same symmetries, okay? Perhaps with more derivatives or with more fields or both. But the effective theory viewpoint is that all the terms that are compatible with the symmetries and involve the fields you're interested in are already there in the Lagrangian. And so for sure, you will be able to absorb any divergence because any possible counter term is already there. Okay? In practice, though, if you generate, if there are some divergences that would require counter terms that scale, based on your power counting are too small to be relevant for what you're trying to calculate, you can simply just throw away the divergence and forget about it. Trust that it would be absorbed by some term in the action, and just you don't worry about it anymore. Okay? Whereas divergences that can be absorbed in the terms that you're already considering in the Lagrangian, those get renormalized exactly, the coefficients you're considering get renormalized exactly as they would in any renormalizable field theory. So from this viewpoint, although one might be a little intimidated at the beginning, it turns out that effective theory are perfectly fine in terms of giving you a prediction that depend on a finite number of couplings that are finite. So incidentally, as a side remark, this is precisely the issue that one encounters in general relativity, where non-renormalizable interactions are forced upon us by diffeomorphism invariant. Okay, so if you start with the action for general relativity, for simplicity, zero cosmological constant, and you expand the metric around the flat space, and you normalize the fluctuations by a power of n Planck, then schematically you find that your action is going to have a kinetic term. I'm just going to suppress here all indices for simplicity, plus h squared. Oh, I cannot write an h without adding a bar, apparently. H squared, the h squared over n Planck squared, and so on and so forth. Okay. So these interactions, these all-tower interactions, are all non-normalizable interactions, and historically, it was because these interactions were non-normalizable that people thought that there was some fundamental obstruction to quantizing gravity. However, in light of what we have discussed so far, it will be hopefully clear that GR makes perfect sense as an effective theory with an expansion parameter that now is energy over the Planck scale. Okay? So as long as you are interested in making predictions at energies that are much smaller than the Planck scale, then GR is a perfectly fine theory. In principle, should be supplemented with higher powers of the curvature, additional derivatives, because as we said, according to our mantra, all terms that are compatible with the symmetries and with the particle content should be there in the action. But in practice, since our usual experiments are conducted at energies much smaller than the Planck scale, all these terms are negligible, and GR works just fine. Okay, this was just a side remark to try to counteract a little bit the bad rep that that GR has as a field theory. Now, of course, when we reach energies of order of the Planck scale, of order of the strong coupling scale, then this effective theory ceases to make sense, and it will need to be replaced by a more complete theory, and that's where quantum gravity comes in, string theory. But as long as you're interested in low energy predictions, this is just perfectly fine. It's as fine as the toy model we just discussed. Okay. So very good. After this aside, let me now show you how renormalizable theories like the standard model come about within this effective theory framework. Okay. And let's look back at our EFT Wilson coefficients. Okay, so these guys here. So the scale of the low energy physics is little m, the mass of the fermions. The scale of the high energy physics is big M, that's the mass of the scalar. And you see that the mass of the scalars enters in two possible ways. It enters in powers of these ratios, like here or like here. Can we write this like so? Sorry. Or like here, or it can enter in the logs. Okay. So if we choose to match at mu equal big M, as we said before, the logarithms just vanish, and the only dependence on the UV scale big M is just in these ratios. Okay. Now, if we take the limit where the mass of the scalar is infinitely larger than the mass of the fermion, which is if we send this ratio to 0, or equivalently, if we keep m squared fixed and send the mass of the scalar to infinity, then almost all the Wilson coefficients in our effective theory will vanish, and the only term that survive are the renormalizable terms. Okay, so we can think of renormalizable theories as what you get if you start with an EFT, and the UV physics is at scales much larger than the other scales of your low energy theory. Okay, in this limit, you can send the mass scale, the UV scale to infinity, and you're left with a renormalizable theory. Okay. And notice that in this limit, the bare, so the coefficients that survive, the Wilson coefficients of the term that survive are what you would call the bare couplings in your renormalizable theory, and are defined at a scale mu essentially equal m going to infinity. Okay. Now, from this perspective, we can also understand why renormalizable theory have this magic property that all divergences can be absorbed in the limit in the coefficients of the terms that are already there in the Lagrangian. And it has to do with the fact that if we were to work within the EFT, divergences generated from loop would come with some powers of 1 over m, m being the UV scale. But in the limit where m goes to infinity, 1 over m goes to 0. So this would be divergences that need to be absorbed in operators that are quote unquote not normalizable. Okay, so this type of divergences would just go to 0, and therefore in this special limit they simply do not arise. Okay, I'm being sloppy here a little with the order of limits in terms of sending m to infinity and dimensional regularizations, but I just want to give you at least an intuitive picture of why a normalizable theory has specials and how they can be thought of as just a very special case of, in general, any EFT.
Riccardo,
all right, so let me
interrupt you because there is a quick question exactly about this. So Sanket is asking, can you repeat what happens to the logarithms as you take capital M to infinity?
Yes, so what I did here was just, I chose to work with a renormalization scale, mu equal capital M. Okay. We said that this is the smart choice for the matching because these logarithms vanish. And when you do that, then capital M only appears in these powers. And so that it's not in logarithms anymore. And so the limit where M goes to infinity becomes regular now. You have only a bunch of things that go to 0 because they're suppressed by large M, but you don't have any logarithms that misbehave.
Okay, he's satisfied. There are no more questions for the moment.
Okay, very good. So then we're gonna switch to another topic, which is something you might have heard of repeatedly, which is the topic of naturalness, and what does it mean for certain Wilson coefficients in effective theories to have natural versus unnatural values. Naturalness has been one of the driving forces in fundamental physics in the last few decades. And so I would like to give you a sense of what is this notion in the context of this particular toy model that we've been considering. And then at the end, I'm just gonna make a few remarks about the implications for physics beyond the standard model and the standard model itself. Okay. So to talk about naturalness, I will use exactly the same toy model, but now I will switch to a different region in parameter space, one where the mass of the scalar is much smaller than the mass of the fermion. Okay. Now, in this case, we can apply exactly the same logic, if you want, that we applied when the heavy particle was a scalar, and say, look, if you're interested in energies that are much smaller than the mass of the fermion, then scattering processes involving scalars are never going to produce fermions by conservation of energy. And you should be able to describe what's going on at low energies using an effective theory that only involves the scalar field. And you can certainly do that. You can figure out what the form of the effective action should be in order to reproduce all possible 3-level processes, and what the one-loop correction to the effective action should be in order to also reproduce all the loop diagrams. And if you focus in particular on the 2-point function, as we did in the case of when the fermion was a light particle, what you find is that the three-level part of the effective action plus the one loop part, a quadratic order must look like so. Okay. So you have, as you will expect, a kinetic term for the scalar, and then you're going to have a mass term for the scalar, and then of course you're going to have all other sorts of operators that involve higher powers of phi interactions. And these coefficients z and m, by matching, they must take this form. Okay? Log of mu squared over little m squared, and then big M squared plus y squared over 4 pi squared, little m squared, 1 plus the log of mu squared over little m squared. Okay. So now, in this region of parameter space, little m is our UV scale, and big M is our IR scale. And you can see that these coefficients have at least one property that you would expect by now, namely the logarithms that appear in them only contain the UV scale as well as the renormalization scale. But there are no logarithms of the IR scale. Exactly as in the previous example, there were no logarithms that involved large M. Okay, now I'm going to focus on the expression for the mass term, and I would like to contrast it with the mass parameter in the previous case. Okay, so previously, namely in the case where little m was much smaller than big M, and we had an EFT for light fermions, the result we found took this form: squared over 16 pi squared, 1 plus little m squared over big M squared, 1 minus the logarithms of m squared over mu squared. All right. Very good. So there is a qualitative difference between these two results in the boxes. You see that for values of mu where we do not have large logs, maybe let me just say that this is the mass of the scalar, it's the mass of the fermion, just so we remind ourselves. Okay. For values where you don't have large logs, the mass of the fermion, the mass parameter, is in general of order little m. And the loop corrections, which correspond to this piece here, are guaranteed to be small because they are suppressed by a coupling y, which we assume to be small to begin with, so we could trust perturbation theory. And furthermore, they're also suppressed by this loop factor of 1 over 16 pi squared. So because of that, we are free to choose m of mu in such a way that it is arbitrarily smaller then the strong coupling scale began. Okay, so this is what happened when the fermion was light. You can choose the mass of the fermions to be as small as you want compared to the strong coupling scale. In the scalar case, instead, this is no longer true. It's no longer true because you see the one loop correction here is not proportional to the mass of the scale itself, but it's proportional to the mass of the heavy fermion. So it's proportional to the UV scale. And so because the mass, this curly M, is just a sum of two terms, unless there are no cancellations, you can expect that M squared S of mu is going to be at least as large as y squared over 16 pi squared M squared. Okay. So whereas there was no lower bound on the mass, this curly M for the fermion, there is a lower bound dictated by the fact that we don't want any fine tuning on the mass curly M of the scalar. In principle, in order to violate this bound, you could choose to, say, tune the three-level contribution and the one-loop contribution in such a way that they almost cancel out and give you a result which is very, very small in the end. But notice that any tuning that you perform would hold only for one specific or a very small region of values of the renormalization scale mu. As soon as you change mu by a relative factor of order 1, this fine-tuning is going to be messed up. And again, you will end up with some curly M, which is at least, which satisfies this bound. Okay. And so for this reason, values of curly M that are much smaller than y squared over 16 pi squared little m squared are considered unnatural. Okay? Because if they can be achieved at all, they can only be achieved for some very particular values of the renormalization scale. Not to mention that this is just a one loop calculation, then you will need to add higher loop corrections. But for now, I'm just gonna stick at with the one loop level, okay? So the fact that the mass parameter of the scalar receives loop corrections that are proportional to the UV scale, rather than, as in the case of the fermion, where the loop correction was proportional also to the higher scale. This fact is known as UV sensitivity of the mass of the scalar, which intuitively just means that the value of the mass of the scalar, the mass parameter, is really sensitive to what's going on in the UV, as opposed to the mass of the fermion. Okay. So there is another way of rephrasing this condition, which, you know, values that satisfy this condition are instead considered natural. A way of rephrasing it is to say that a sufficient condition for this equation to be satisfied is that big M squared be larger or of the order of y squared over 5 pi squared, 4 pi squared times the UV scale. So this way of phrasing this issue of naturalness versus unnaturalness is what usually gives rise to the notion of technical naturalness, which is the idea that the values of Wilson's coefficients shouldn't be altered significantly by loop correction. Change much by loops. Right, you see, so this part here was essentially the three-level contribution to the mass parameter, and this is the size of the loop level contribution. And when demanding that the three-level contribution is at least as large as the loop level contribution. Okay? So that effectively our Wilson coefficients admit some well-defined perturbative expansion. Now, this criterion of technical naturalness is believed to be a criterion that self-respecting effective theories should satisfy. Okay? So we'll come back to it in a moment in the context of the standard model and see what that implies. Before we do that, though, let me just address or prevent one question, which is why can we understand why the fermion was so lucky that it wasn't UV sensitive, whereas the scalar is? Right? And there is actually a fairly simple explanation in this case. And it has to do with the fact that in the limit where in our full theory, we send the mass of the fermion to 0. The full action acquires an additional symmetry. Namely, a symmetry where psi goes to gamma 5 psi and phi goes to minus phi. So the mass term, when it's there, breaks this symmetry. And so, on the other hand, when it's not there, loop corrections should preserve the symmetry and therefore cannot generate a mass term. Okay, the one loop part of the effective action cannot contain a mass term if the tree level didn't, because it would mean that the loop corrections would break a symmetry. Let's forget about anomalies for a moment, which are not a consideration in this particular toy model. So because of that, any loop correction that the mass parameter for the fermion receives must be proportional to the symmetry breaking parameter itself. Okay, so delta M must be proportional to little m itself for the fermion. And so this idea, this example is a particular case of what is known as symmetry protection. And it's the idea that some Wilson coefficients in an effective action are allowed to be as small as you want if setting them to 0 gives you a new symmetry. Okay. So this condition is certainly sufficient to achieve technical naturalness. Okay, so a small mass for a fermion is technically natural because it is symmetry protected. But it's not necessary. Okay, there are Wilson coefficients in many effective theories that do not receive loop corrections, for instance, because they're protected by topological reasons. Even though setting those coefficients to 0 are not wouldn't give you any extra symmetry. So this notion of naturalness due to symmetry protection was first proposed by Toft. Okay, and in fact, it's also referred to very often as technical naturalness, even though here I'm trying to draw a distinction and claim that technical naturalness is a broader concept, if you want. And symmetry protection is just one way to achieve it.
Riccardo, we have a quick question. So David is asking, is there a way to show that the same conclusions hold in a non-perturbative regime?
Which conclusions in particular? So maybe
I guess he was referring to the fact that the scalar is always sensitive to the heavy scale. The scalar mass is always sensitive to the heavy scale.
So it's a good question, because you know, if you have a okay, you would be interested in using non-perturbative methods, say if you are in a theory that is strongly coupled. Okay? In which case, if your theory is strongly coupled, it's not even clear in general the degrees of freedom, the fields that you write in your Lagrangian are not going to correspond to the relevant degrees of freedom at low energies. So an example of that is QCD, right, where at very low energies the good degrees of freedom are mesons and are not the quarks. So it's a good question. I'm not sure how to address it, how I would go about showing that. In practice, most of what I'm saying is is motivated by the Higgs. So yeah, I'm not sure I'm able to address your question as well as I would like.
So there is also another question from Francesca. It would be nice to get some reference for the demonstration of the symmetry protection mechanism. Is it a theorem or something?
So it's not really a theorem, but if you want a reference, I think the original paper by Toft on chiral symmetry breaking, and I think it's very it's an easy read, and it's very well written. So I would definitely look at that. And I don't know if there is a way for me to share a reference at some point, or I can send it to the organizers, or.
Yeah, you can send to us so we can put it online on the website.
Okay, perfect. Yeah.
Okay. So, and there is also a third question by Daphne. What happens if you have IR divergences instead of UV divergences? Don't you renormalize? What do you do with those divergences in EFTs?
Okay, very, very good. So IR divergences are a completely different kind of worms. So UV divergences are just a manifestation of the fact that your theory is only valid up to some scales, and you are sort of hiding your ignorance about physics at the microscopic scales in the coefficients of your effective Lagrangian via the renormalization program. Instead, IR divergences typically are a much more serious issue, and oftentimes are a manifestation of the fact that the quantity that you're calculating is not really a physical quantity. So an example of that is, for instance, in QED, if you consider scattering processes between fermions, where also one photon is emitted, you have an infrared divergence in the limit where the photon becomes very, very soft. And that has to do with the fact that when the photon becomes very, very soft, it becomes a hard, sorry, pun not intended, it becomes difficult to tell apart processes where you're emitting one photon, two photons, three photons, and so on, if they're all very soft. And similar issues you encounter in collinear divergences. And so in the case of QED, for instance, you deal with these IR divergences by, there are a couple of ways of doing it. You can do it by resumming all these processes where you emit 1, 2, 3, 4 photons and so on, or by considering initial and final states that are dressed. A nice discussion of this is on, you can find it on the textbook of Peskin-Schroeder. So in the first approximation, I think it's important to keep in mind that IR divergences and UV divergences are very different problems. Okay.
Okay, so we have another question that may be interesting now before you move on to the next subject. So if Oppo is asking, if I understand correctly, vector currents don't get renormalized because their anomalous dimension vanishes. That means such Wilson coefficients don't evolve with scale. Is it true that the divergences arising in such theories won't get removed?
I'm not sure I understand. I'm not sure I understand the question, so I wouldn't know how to answer it. I don't know if maybe Enrico.
No. So I agree that vector currents, conserved currents are not renormalized because of current conservation.
Yeah.
But yeah, I don't know, Oppo, I don't know what you mean when you say that these Wilson coefficients don't evolve with scale. Which Wilson coefficients are you talking about? Maybe if you can qualify a bit better
maybe we can
the question later on, we can come back to this
at the end. Yeah, I think.
Yes.
Okay. Okay. So if there are no more questions, then let me just conclude with a few comments about naturalness. And the first comment that I think it's important to make is that this issue of UV sensitivity is not a problem of the effective theory. Okay, it's not an artifact of the fact that we went from the full theory to the effective theory. It's also a problem that you could have talked about already at the level of the full theory. Okay. And so let me say a few words about that. Now, I talked on and on about how the MS bar scheme and dimensional regularizations are very convenient. Perhaps the only drawback is that the mass parameter that appears in the action beyond 3 level is no longer the physical mass of your particle. Okay? But instead, the physical mass is defined as the location of the pole in the propagator of the corresponding field. Okay. So okay, I should say that the mass is always the location of the pole, but in MS bar, yeah, M is not the physical mass. Maybe that's a better way of saying it. It's different from the physical mass. Okay. But including one loop corrections, you can calculate the propagator, and then you can calculate perturbatively what the location of the pole is. And for the scalar field, you will find that the location is a combination of all your couplings in effective theory, and it has the three-level mass, and then it has some terms that looks like so, okay, times some other factors. And at one loop level, we can replace this mass of the fermion with the physical mass of the fermion, because that would be the difference is just of higher order in the UCAV coupling. And so once again, you can see that in order for the physical mass of the scalar to be much smaller than this combination, now expressed in terms of the physical mass of the fermion, you need, again, another fine-tuning. So this is a way of seeing the UV sensitivity at the level of the full theory rather than at the level of the effective theory. Now, the second comment I want to make is that this issue of UV sensitivity is often discussed or associated with the issue of quadratic divergences. Okay. So the prototypical example is, say, if you have some phi to the fourth scalar theory, and you calculate a loop diagram of this form, then this is going to look like so. And the idea is that this is UV divergence. If you cut off the divergence with a cutoff, you get something that grows with the cutoff squared, and it's going to correct the mass. And this quadratic divergence, if you want, it's going to be absorbed in the mass of the scalar. Okay. Now, as I try to emphasize over and over again, working with a hard cutoff is not a smart choice in the context of effective theories, because it messes up your power counting. But there is, of course, a grain of truth behind the fact that the UV sensitivity is often discussed in these terms. And this quadratic divergence can be viewed as one form of UV sensitivity by thinking about the imposition of a cutoff at momenta of order lambda as some particular type of UV physics. Of course, it's very much a fake UV physics where you erase all the Fourier modes with k larger than lambda, but it's a form of UV physics nonetheless. Okay? So from this viewpoint, you can view this quadratic divergence as as the fact that the mass of the scalar is sensitive to the UV physics. But it's important to keep in mind that this cutoff that gets imposed to regularize integrals that otherwise would be with divergence, would be with UV divergent, is a different beast from the strong coupling scale that tells us when our effective theory breaks down. Okay, and the two things should not be confused. One is a mathematical trick, the other one is instead of a physical scale. Very good. Now, the third comment comes with a disclaimer, which is that many people have, everyone have their own slightly different viewpoint on naturalness issues. So what I said up until now is pretty much agreed upon. Now we're gonna enter the territory where I'm gonna share a bit my viewpoint, and but I think it's okay because it's perhaps a way of also reminding you as young scientists that are entering the field that you should always be critical of what you read in the literature, and you should, part of growing up as a physicist is figure out what your viewpoint is on the main open problems in the field. Okay, so you should take what I'm going to say with a grain of salt, as well as anything else you read on the topic, and you should try to come up with your own understanding of this issue. Okay, so with this disclaimer aside, let me say that I think one way of seeing naturalness is as a constraint that effective theories place on their possible UV completions. Okay? What do I mean by that? Let me write again this condition that I wrote before. Okay. Now, as I emphasized, this places a lower bound on the mass of the scalar in the EFT, which depends on the strong coupling scale of the theory, and also depends on this coupling Y, which measures the strength of the coupling between the heavy states, fermions, and the light states, the scalar. Right? If instead of having a heavy fermion, we would have had a different particle content at high energies, the explicit form of this bound would have looked a bit different. So from this viewpoint, this constraint is something that qualitatively it's going to be there also without a UV completion, but its explicit form depends on the particular choice of the UV completion. Right? And so it's only when you also know the UV completion that you can check whether or not your theory, which in this case would include both the scalar and the fermion, appears to be technically natural or not. Okay. So I'm trying to draw a contrast between naturalness as a constraint that EFTs place on their own UV completions, and say constraints that one could derive on the EFT by making some assumptions on the possible UV completion. Okay, I'm not going to go much into that, but let me just give you a very simple example. There can be low energy effective theories that are perfectly consistent, but that in practice cannot be realized if you make certain assumptions about what happens in the UV. Perfect, thanks, Enrico. And an example of that is a non-relativistic theory where there are bosonic fields with spin and a half. Okay. From a non-relativistic viewpoint, there is no problem whatsoever, as far as I know, with this picture. But once you try to embed this theory in a relativistic theory, relativity provides us with a connection between spin and statistic that tells us that fermions must have half-integer spin and bosons must have integer spin. Okay? So this is a constraint on the, in this case, on the particle content of low-energy EFTs that comes when we know that, say, or if we assume that our UV completion must be Lorentz invariant. Okay, and there are other constraints on values of the Wilson coefficients that people have been derived in the literature by making assumptions about the possible UV completions of effective theories. Okay. Now, what's the relevance of naturalness when it comes to the standard model? Well, the standard model plus gravity has two UV sensitive parameters. Okay. One is the Higgs mass parameter, and the other one is the cosmological constant. And each of these poses its own problem for model building and for our understanding of fundamental interactions. The UV sensitivity is of the Higgs mass is known as the hierarchy problem, whereas the UV sensitivity of the cosmological constant is known as the cosmological constant problem. Now, of course, there are many good reasons to think that there should be new physics above the weak scale. There are many, there are many arguments why we would expect such a thing. One of the most robust, from my perspective, going back to gravity, is that we said general relativity is an effective theory which at some point breaks down at energies of order of the Planck mass. And at those energies, you would expect other particles or other states or other physics to come in, exactly as in our toy model, when we reach energy of order of the mass of the heavy particle, we encounter this new particle. And so at the very least, this suggests that you should have new physics coming in at the Planck scale. And therefore, based on the argument I gave in this toy model, you would expect the mass parameter of the Higgs to receive corrections of order of the Planck mass, which would be the mass of these new states. Now, in practice, one of our best ideas for how to UV complete general relativity is string theory. And as far as I know, there is no clear-cut calculations, matching calculations that one can do from string theory to the standard model to calculate what the mass parameter of the Higgs should be. So, although everything we have, everything we know about effective theories and about particle physics seems to suggest that there should be a fine-tuning problem associated with the mass of the Higgs. in practice, the way I view the UV sensitivity of the mass of the Higgs is just as a constraint on possible models of physics beyond the standard model. Meaning that if you want to embed the standard model in a UV completion, and you add particles and degrees of freedom and higher energies, you better do it in such a way that that these new particles do not destabilize the value of the weak scale. Okay? Do not give excessively large loop corrections to the mass parameter of the Higgs. So it makes the life of model builders very difficult. Okay? But whether or not it's really a problem in the sense, an aspect of nature that we don't understand, I think it's still a little early to tell. Contrasted with the cosmological constant problem, where we know what physics looks like at scales larger than the size of the universe. Okay? We know we have electrons and quarks and other leptons, and any state, even the lightest particle, like even the electron, for instance, would give a loop correction to the cosmological constant, which scales like the mass of the electron to the 4th power divided by the Planck mass squared. Okay? So even for the electron, this is many, many orders of magnitude larger than the observed value of the cosmological constant. Okay. And so here, there is no room. We cannot hide about the fact that, oh, maybe the UV physics is something we don't understand, and but eventually things will conspire so that there is no fine-tuning. Here, we know what the quote-unquote UV physics looks like compared to the scales of the cosmological constant, and it seems to give loop corrections that are just way too large. And so this state of affairs have pushed people to consider the fact that perhaps there might be new organizing principles at play in the theories of fundamental physics. One of the most popular one is the anthropic principle. More recently, also mechanisms of cosmological relaxations have been considered, where essentially it's the evolution of the universe that relaxes the value of the cosmological constant to the very small value that we observe. Okay, so this, in a sense, goes a little beyond the paradigm of just effective theories, and these are certainly interesting possibilities. But it remains that within the pure context of effective theories, the cosmological constant is a very, very, very difficult problem to solve. And hopefully, one of you will solve it. All right, let me stop here for now and see if there are more questions.
Thank you, Riccardo. So guys, no pressure, but we expect you to solve the cosmological constant problem now.
Exactly.
Okay.
By Friday.
By Friday, yes, in the exercises, please.
Yeah.
So we have a remark and a question from Boris. So the remark is that EFTs with a cutoff regulator can be formulated, for example, the EFT for nucleon-nucleon interaction.
Mm-hmm. You can work with cutoffs in general, but as I said, if you want to be systematic about and have control and assurance of the fact that the terms you're neglecting are smaller than the terms that you're keeping, typically the safest way to do that is to work in dimensional regularization.
And then there is a question, always from Boris. Does UV completion imply a UV non-trivial fixed point?
It depends. It may or it may not. It depends on whether the UV completion is is a partial UV completion or not. So sometimes you might be able to raise the cutoff or the strong coupling scale by adding some states, but raise it only up to a certain amount, and then you need more states to come in. So in that case, yeah, that's the case where you wouldn't have a fixed point.
So more questions for Riccardo? Okay, so there is a question from Alison who is asking, are there other approaches to solving the hierarchy problem beyond SUSY?
Yeah, so there is, one of the most popular is the idea of compositeness. So, if you want the, actually, probably tomorrow, we will see how it is possible to protect the mass of the scalar if the scalar is in a first approximation a Goldstone bosons associated though with a symmetry which is not exact. So in that case, the symmetry breaking parameter, if small, will give a small correction to the mass of the scalar, but this mass will still can be parametrically smaller than the strong coupling scale of the theory. So that is probably the simplest way of achieving a light scalar, I would say.
Yes. If I may just add, there is also an analogous of the mechanism that Riccardo was mentioning to relax the cosmological constant that was applied in the case of the Higgs mass, which is the original relaxation idea.
Yeah, exactly.
Yes. So there are many mechanisms
Absolutely.
beyond SUSY. So next week we're going to have a whole set of lectures on beyond the standard model physics. So I guess Charco will cover most of them. So more questions for Riccardo. So there is a question from Beatrice. The UV completion to EFT needs not to be a field theory at all, right? For example, it can be string theory.
Yeah. So it's certainly, at scales beyond the Planck scale, then we could have something like string theory. So here, for the purposes of just introducing the main concept, I play with a simple toy model where you have a field theory in the IR and the UV, but it could be situation could be certainly more complicated. Right? So, for instance, you can have a field theory, say in condensed matter, that describes sound waves or phonons, but then when you go at very high energies or small length scale, you find that the UV completion is just having a lattice of atoms. So yeah.
So there is another question about the IR divergences from Anupam. So the question is, what if when we have both IR and UV divergences, what if we have both IR and UV divergences in our theory? Can we apply EFT?
Yes, in general, yes. As I discussed, I don't remember, I think it was maybe during the Q&A or also, but anyways, so your life becomes more complicated when you have IR divergences, because your physical quantities eventually should not have any IR divergence. But in principle, the same framework can be used with more care. I'm not going to discuss too much about IR divergences in these lectures, but there are certainly other there are other resources available. Some of them, I cite them also in the notes.
Okay. More questions? We have time for one last question, if you guys have it. Otherwise, of course, tomorrow Riccardo will be still around for the question and answer session.
Sure.
Okay, so I don't see any more question, Riccardo. So thanks a lot for the very nice lecture. So thank you everybody for the participation. It was again a very nice day, a very stimulating day, and see you tomorrow. So let me just remind you that tomorrow morning we're going to switch the order of the lectures. The first lecture will be given by Rogerio, will be cosmology, and the second one will be given by Andrea, and it will be the standard model. And then third one in the afternoon